Hello everyone, and today we'll be talking about computer vision. Computer vision is one of the most difficult problems we are facing today in robotics. The general idea of a robot observing and understanding its environment is abstractly defined at best. The reason cameras are being so widely adopted is because they are cheap and provide a large amount of information about the world. The key difficulty is properly parsing this data to provide answers to the questions our robots are asking. The core idea behind what we will be discussing today for computer vision is trying to use images to generate some important model of the world. When I say model, I mean something like what we see here. In this image, we are trying to read a license plate. We have some model of what the alphanumeric characters should look like, as well as how they should be arranged in the image. Using what we know about the world, otherwise known as domain knowledge, we can determine useful properties about our image. When we use our domain knowledge, we bias our algorithm to what we think the model should be. While this is entirely the point, it can lead us to problems. An example here is on the right, a European license plate. While this is very similar to what you see on the left, the separation in the middle breaks the property that we were using previously. Before, we had 7 digits that were laid out next to each other. Here now we have 6 digit with a break in the middle. If we are using the same model to look for 7 digits in the 6 digits, we have a problem because this character right here is not a digit that we should be scanning. This is often the issue we face with computer vision. There's a lot of variability that we need to account for. A great example of this is in these slides. What do you see in this slide? Probably a bunch of chairs, right? But look how different each chair looks. You've used a very strong model of what a chair is to determine that these are chairs. If I made you explain exactly what parts of the image made you think it is a chair, it would be very difficult to be specific. Like maybe you could say something like it has legs, or a place to sit, or something else. But I would argue back that is still a poor definition. A table would fit that. It has legs and I can sit on a table. Humans are very good with extracting semantic meaning from abstract representations. For example, what do you see here? Probably something like a dinner table with a light above it, surrounded by chairs. But what about these blotches after I remove them from the image tells you exactly what they are? Is it the color, or the shape, or the relative distance between objects in the scene? Likely all of the above. As you can see, we have some chairs on either side of a table, so we're kind of getting an idea of like a dinner table, where you have chairs and it makes sense to have a light above it, so we can fill this abstract representation in with a light. You're using a lot of semantic understanding of what should be happening in the scene based on essentially a bunch of different properties to figure out what you're actually looking at. So now what happens if I take that context away from you? What do you see in this gray blob? Probably nothing. You have no idea exactly what this is. But if I give you more context, if I put it in the context of an image, what do you see? Probably like someone's phone or a plate in front of him or something that he's working on, right? You use the idea that there's a person in the background to figure out what this gray blob should be. Now what do you see in this gray blob? What happens when I give you another image? So here we see a building in the background and there's a street, there's a person walking, and then you're seeing a car. So by marking this, you now think that that gray blob is a car. Now what do you see in this gray blob? So now that I've marked it on this image with more context, you're like, oh, well that's probably a shoe because I see some legs and there's a person bent over. What you've actually done is associated the exact same gray blob with 3 different objects based on what you see around it. Computer vision, like robotics, is a conglomeration of a lot of different subfields. There are subfields for understanding images as a physical phenomenon like optics, as well as particular applications like medical imaging. One of the subfields getting a lot of attention right now is machine learning. That is because it helps us solve the underlying issue of parsing a large amount of complex data. We will not be covering machine learning in this course, but we will be covering the basic building blocks that are used to create state-of-the-art models. When you think of a camera, you probably think of something like this. We have some light that's coming out of the sun or whatever else our light source may be that is illuminating some scene. Based on that, we have some sensor that reads in that light information, processes out, and generates some digital image. So this is converting an analog signal, which just means it's a continuous signal, to a digital signal, which is discrete. Whenever you convert from a continuous signal to a discrete signal, you lose some information. As we can see here, we have these really clean edges on this 8, but when we convert it to a digital image, we're interpolating, we're doing some combinations to figure out what each pixel should be, because there's really lots of colors that could be representing that single square. Now the important thing to remember is that you can almost never recover the true analog signal from some digital representation. So here we have some very similar digital signals, but as you can see, the analog signal that's generating them is very different. This is kind of the problem that we run into a lot with computer vision. The most common model we use for the physical phenomenon that is image capturing is the pinhole camera. So this is where you have some barrier that blocks all light, except for a single ray for each location. So you can see here this red object at the top, or this blue object, is sending out beams of light in all directions because it's reflecting the light that's coming from some light source. But our magical pinhole camera only allows in a single ray from every single point that represents us on this back image plane. And the pinhole camera gives you an inverted image. The pinhole camera is the simplest camera model that exists. It has no lens, it just has a single tiny opening and then a barrier. So now if we include a lens, what we can see is that we can take in more rays of light and it will reflect it to the exact same location. So if I take this lens and I shift it back or forward, this is what we know as changing focus, essentially. So as I move this lens, these light rays will reflect to a different location on the back image plane here. And if all the light rays do not converge to the same point, you have something that's out of focus. So let's talk about a couple of important camera properties. So the first is resolution. This is the number of pixels in an image. We have aperture, the area of light that can enter the camera, so essentially the size of our opening. And we have field of view, which is how wide of an angle we can see in our camera. So you can think of it like this. And then we also have shutter speed or exposure time, and that is how long it takes us to acquire an image. You may think that a digital image is a representation of a single instance of time, but it actually takes a while to acquire the image, so it's not. And this is what the shutter speed represents. So an issue that you often get in robotics is this thing called motion blur. And this means if your shutter is taking too long, what you'll get is the image will be taken at slightly different times for each different pixel, and you'll kind of get this smearing effect across the image. This is a more drawn out example of what shutter speed would do. If I have a 1/5 of a second shutter speed, I get this very crisp image. And if I have a 6-second shutter speed, I get this very blurry, washed out image. The other important property is focal length, and focal length represents the distance from the lens to the image plane. And here we can see as we change the focal length, you zoom in on the object. So with a very short focal length, what we see is a very wide view of the area, but with a very long focal length, we see a very focused image. So often in robotics, what we're trying to do is maximize our field of view. So that corresponds to using a very shallow focal length. Obviously this depends on application, but usually something like a 600mm focal length would be very aggressive because you'd only be seeing 4 degrees. And usually we have robots that are trying to move around the world and see everything at the same time. So one of the ways we try to get around this is you can see we're kind of limited by what the field of view is based on our focal length. We can use this thing called a fisheye lens. Fisheye lens does is it warps the image so we can actually get a larger representation of what we're seeing. You see this 15mm line, which is actually encompassing more of the image than even a shallower focal length would be the 10mm, which is taking in the whole image. So using fisheye lens ends up with this problem. We have this thing called camera distortion. So this is when you have a little bit of a fisheye right here, what we can see is this checkerboard pattern is actually, should be flat. You should actually have parallel lines between them, but you can see how they're bowing around the center of the image. So what we're looking at is barrel distortion. And before we can use this for processing, we actually have to rectify this distortion and get it back to an image that looks like this. Because what that's going to do is going to take lines that are no longer straight and make them straight. And this is really important for a lot of applications. Next thing we talk about is aperture. So that's the size of your opening. And as your aperture gets smaller, what you get is a darker image. And as your aperture gets larger, you get a brighter image. There's actually some relationship between how wide your aperture is and the amount of focus that you can have on your image. So typically in robotics, we're looking for a smaller aperture. So this shows the relationship between aperture and shutter speed. So shutter speed decreases going this direction and aperture increases going this direction. So we can see is if our camera lens is essentially open for a shorter period of time, that would correspond to a faster shutter speed or less time that it's open. You get a darker image because less light is able to get in during that time period. But if you increase the aperture, so you have a wider opening and you can let more light in at the same time, you get back to a reasonably lit image. If you have too slow of a shutter speed and too high of an aperture, you end up with a very washed out image. If this is too fast and this is too low, you end up with this very dark image. And typically what you're looking for is something with a very fast shutter speed, so you reduce motion blur, but an aperture wide enough that you see everything you need to see in the image. So now that we've covered some important properties of cameras, we can look at color. So you're probably very familiar with how we represent color. So digital color images are based off of 3 different channels, red, green, and blue. Each pixel has a corresponding value for each of the 3 base colors. Each RGB value is a different collection of these colors, and if all the values match between 2 pixels, they are the same color. So if I have something that has the same red, green, and blue values, that means those pixels are the same color. We know from physics that what we perceive as color is actually a very small band of the electromagnetic spectrum. This graphic shows that spectrum as well as the human sensitivity to each band down at the bottom. Notice that we perceive different bands with different sensitivities. This causes an issue when we start digitizing colors. So if we take two different, essentially, colors on this visible spectrum and we convert them to RGB using some camera, what we can actually get is the exact same RGB values, because RGB values are based on how humans perceive color and not on the actual values from the electromagnetic spectrum. The important thing to remember is that since we are often working in RGB, it does not matter that we're getting different values in this spectrum. While the RGB color system is convenient and widely used because of it, there are other color spaces. Each space is better or worse at determining specific things. Here you can see the HSV spectrum. It stands for hue, or the color, saturation, or the amount of gray in the color, or value, which represents the brightness. This space is good for when we are trying to separate the same colors at different brightness. We will be using this later when we do an in-depth example of color filtering. The final thing to mention about computer vision is how much data we're talking about. As we can see here, with a very small image of 128 by 128, we still get about 50,000 values that we're actually looking at. On something like a 4K camera, you'll get something like 24 million values that you have to look through and determine what they mean. This is a large amount of data. Overall, computer vision is an important tool in the roboticist arsenal since it provides a high density of information. Unfortunately, there is no free lunch, and the large amount of data is difficult to understand.